Okay, so then I'm very happy to introduce our speaker for this week. Pablo is an expert in electronic hydrodynamics, and in particular, actually, he will talk about one of his recent works in hydrodynamics of Dirac and Weyl semimetals. So please, Pablo, you can start.
Thank you very much for the introduction. My name is Pavlo Sukhachov. I am a postdoctoral associate at Yale University, Yale Prize Fellow. It is a pleasure to give this seminar today. The topic of my talk is hydrodynamic instabilities in Dirac and Weyl semimetals. This talk is based on our papers written together with my collaborators, Eduard Gorbor and Igor Shavkovy. So to start with, let me briefly discuss the systems that we are interested in, Weyl and Dirac semimetals. So recently, these materials appeared and quickly moved to the forefront of both experimental and theoretical condensed matter studies. The low-energy Hamiltonian of Dirac semimetals is given by the following rather simple expression. So it is the same as a conventional Dirac Hamiltonian for relativistic particles, albeit it has a vanishing mass. As you can see, there is no mass here. Also, it has a speed of light replaced by the Fermi velocity. And these sigma matrices act not on the real spin, but rather on the pseudospin, effective pseudospin degree of freedom. And of course, K is the momentum here. The energy spectrum of Dirac semimetals is rather simple. So it's just a three-dimensional cone where valence and conduction band intersect at a single Dirac node for this simple case. We have parity inversion and time reverse asymmetries preserved. Therefore, the cone is doubly degenerate. It is composed of two Weyl fermions of opposite chirality that overlap. On the experimental side, Dirac semimetals were discovered in several compounds, including bismuth antimony alloy, trisodium bismuthide, cadmium 3 arsenic 2, zirconium pentatelluride, and a few others. In case of Weyl semimetals, the situation and spectrum is a little bit more complicated and more interesting. In particular, we need to break as a parity inversion or time reverse asymmetry in Weyl semimetals. This will lead to a splitting of each of the Dirac fermions into two Weyl fermions of opposite chirality. In this case, for example, we are breaking all symmetries and we are separating Weyl fermions in momentum space by this parameter 2b and in energy by parameter 2b0. Unlike Dirac semimetals, Weyl semimetals are usually called topological semimetals. Their non-trivial topological properties are quantified by Berry curvature. In particular, in the case of such simple model, each of the Weyl fermions is a monopole of the Berry curvature in the source or sink of the flux of the Berry curvature. This immediately leads to the fact that one cannot remove a single Weyl fermion by leaving the other intact because the total flux of the Berry curvature through the Brillouin zone is conserved. It's just zero. But if we remove one fermion, then we will get a non-zero flux. Therefore, usually people say that Weyl fermions are topologically protected. On the material side, Weyl semimetals are discovered, and for example, in transition metal mononucleotides, magnetic compounds, for example, this compound, European cadmium 2 arsenic 2, is believed to be one of the most ideal version of the Weyl semimetals with just two Weyl nodes. The properties of Dirac and Weyl semimetals are rather interesting, especially in view of their non-trivial topological properties and relativistic-like energy spectrum. In particular, we have non-trivial interaction effects where we can pair quasi-particles from different and the same Weyl nodes. Non-trivial topology of Weyl semimetals is also manifested in Fermi arc surface states, which have non-trivial transport properties and are manifested in specific elective modes. Also, transport properties of bulk Weyl semimetals are exotic. Particularly, they can demonstrate the anomalous Hall effect, which is a Hall effect without any external magnetic field. Also, various anomalous thermal responses are present here. Superconductivity is non-trivial in Weyl semimetals, where again we can pair quasi-particles from the same and different Weyl nodes and realize the conventional BCS or Larkin-Ovchinnikov full deferral states. Finally, Weyl semimetals allow one to realize unusual pseudo-electromagnetic fields by applying strains or non-trivial magnetization textures. In this case, these pseudo-electromagnetic fields act on quasi-particles of opposite chirality as if they have opposite electric charges. So there are many properties, there are many interesting things to talk about if one wishes to consider Weyl semimetals. In this talk, I will focus mostly on transport properties in a very specific and interesting transport regime, namely electron hydrodynamic regime. Well, I think that this regime requires some explanation because usually when we talk about transport in materials, we don't talk about hydrodynamics. The conventional transport regime, Drude regime, occurs when the momentum relaxation length scale, which is a length scale connected to the scattering on impurities, phonons, various disorder in material, is the shortest length scale of the system. So it's much shorter than the size of the sample and the momentum conserving length scale that corresponds to the scattering of electrons between themselves, electron-electron scattering. So this non-hydrodynamic regime roughly corresponds to this figure where electrons bounce from impurities and phonons like pinballs. In the ballistic regime, they can, of course, bounce from boundaries of the sample, but still, in this case, the interaction would be quite weak, and this transport regime we know rather well. In the 1960s, however, Rayleigh-Benard conceived that it is possible to have a regime where electrons interact strongly and form something that is reminiscent to fluid, electron fluid. Such fluid flows through the sample and relaxes its momentum mainly due to the scattering of the boundaries. In this case, the current profile of such fluid is reminiscent to that of the fluid that flows through the pipes. We know this Poiseuille regime of current flow, for example. However, this hydrodynamic regime requires one to have a momentum conserving electron-electron interaction length scale to be the shortest length scale of the system. This case, however, requires rather pure materials or materials with strong electron-electron interactions. So for a long time, it was assumed that while being interesting, this regime is quite far from being realizable in experiments. First signatures of electron hydrodynamics were observed only relatively recently in the 1990s by de Jong and Molenkamp. In particular, they were able to observe the so-called Gurdjieff effect, which is a decrease of the resistivity with temperature in the hydrodynamic regime. Well, in short, it could be explained as follows. Usually, we know that conductivity grows with the relaxation time. In the hydrodynamic regime, however, the relaxation time should be replaced by the length scale squared divided by the electron-electron interaction time. It's just like a diffusion of electrons through the soup of electrons, other electrons. In this case, since the electron-electron scattering time decreases with temperature, we have conductivity that grows with temperature. Therefore, the resistivity decreases. Several years later, the viscous contribution to the resistance of two-dimensional metal palladium boltate was observed by Philip Moll and other co-authors. However, electron hydrodynamics came to its fruition with the rise of graphene, which is a very good platform for observing various hydrodynamic effects. In particular, several effects were proposed and measured experimentally, such as negative non-local resistance and formation of electron fluid whirlpools, high resemblalistic transport in graphene constrictions. Also, the non-trivial Poiseuille flow was visualized by Hall field profile and stray magnetic fields. To give some feeling of these experiments, let me briefly discuss this negative non-local resistance, what it is and how it can appear. So in conventional ohmic regime, where we ignore, for example, viscosity of our electron fluid, we can easily do this theoretically, just turn on the of viscosity term. But on experiments, for example, we can take a disordered graphene ribbon of finite widths and apply contact at -x0 and +x0. In this case, we will have a more or less conventional drop of electron potential as you can see here. And if we measure voltage difference between, let's say, 0 point and say this point, we'll have a very specific voltage drop. It will be positive in these definitions. However, if we include the electron viscosity, then the flow of electrons will strongly change. For example, you can see here there are several qualitative changes compared to the case with vanishing and non-vanishing viscosity. First, there are whirlpools that form near contacts. Second, we notice that there are regions where negative potential appear instead of the positive. Therefore, if we are measuring our surface or edge resistivity by measuring the voltage drop between 0 and this point, we will observe not a positive, as we had here, but a negative voltage drop. And usually this is what is called negative non-local resistance, just a negative voltage drop. And this effect was indeed observed experimentally in graphene. So here I'm showing the phase diagram, transport phase diagram, where the region of negative non-local resistance is shown by this blue long-shaped regions. A few interesting things are of order here. First, we notice that at small charge densities in graphene, we don't have this hydrodynamic regime. Indeed, in this case, a different regime, which is called Dirac fluid regime, is realized. Well, while being interesting, it's a different story, and I don't want to spend much time on it. But another interesting feature is evident from this diagram, is that electron hydrodynamics appears only in a finite range of temperatures. As you can see here, there are two regions that form boundaries between negative non-local resistance and positive non-local resistance. Indeed, at small temperatures, our electron-electron collision length scale is rather large, and we are in disordered regime, whereas the electron impurity collision length is the smallest length scale of the system. When the temperatures are large, then we are scattering on phonons. So electron hydrodynamics is also unrealizable in this case. Finally, the formation of negative potential regions was visualized in Gall-arsenic heterostructures. You can see here. Indeed, near contacts, one can see regions where the voltage drop changes. Here, so in view of the reminiscent to the theoretical prediction, these people claimed that they observed electron hydrodynamics in Gall-arsenic heterostructure. However, so far I was talking about graphene and various two-dimensional structures. What about 3D? Recently, some signatures of electron hydrodynamics in Weyl semimetals, three-dimensional Weyl semimetals, were observed in wolfram phosphorite 2 by Goose and other co-authors. So they were able to measure transport properties of a wire of a Weyl semimetal and change its width. So as you can see here, the experimental step is rather simple, and they were able to etch the wire. So they found the following interesting feature. When the temperature is large, the resistivity of the wire was not a function of its width. Well, something that we do expect from even school level physics. Resistivity is a property of a material, not a sample. But for sufficiently small temperatures, they observed the dependence of the resistivity on the width of the wire. And the exponent of this dependence exactly matched the exponent predicted from the hydrodynamic regime. Exactly matched the exponent for the parabolic-like profile here. And that was a signature that allowed them to claim that they observed electron hydrodynamics in Weyl semimetal. Very recently, another type of experiment was able to visualize the Poiseuille profile of electric current in a film of a Weyl semimetal. So by using the scanning magnetometry microscope, the authors of this paper were able to measure the stray magnetic fields. So essentially, what did they do? So the experimental step was quite simple. So it's just a film of a Weyl semimetal with gold contacts, and they used scanning magnetometer microscope with a diamond tip to measure stray magnetic fields around this sample. These fields were created by electric current. In this figure, I'm showing essentially two measurements that were performed around contacts, gold contacts, which are assumed to be non-hydrodynamic because gold is still quite disordered, and around materials themselves, which we believe is hydrodynamic. So as you can see from this figure, for example, measured a normal component of the magnetic field agrees very well with experimental data. So these solid lines agree well with experimental dots. And furthermore, one notices that qualitatively, the shapes are quite similar, both for gold and both for Weyl semimetal. In the case of the longitudinal component of the magnetic field, there is a larger difference between gold and Weyl semimetal, and also we notice a large agreement with between the experimental and theoretical data. However, this small disagreement between shape of curves actually leads to a large difference between the restored profiles of the current. So essentially, by solving the inverse problem, this group was able to obtain the current profile, which generates the corresponding magnetic field. They found that in the case of gold, the profile is simple, just a square shape profile, which we do expect for the ohmic regime. In the case of Weyl semimetal, we have a parabolic-like profile. And only in this case, we have a more or less good agreement between experimental data and numerical calculations. Therefore, the formation of the Poisson profile was also experimentally confirmed in Weyl semimetal.
Can I, sorry, interrupt you 1 second?
Sure.
I probably said fast. So how are the surface states accounted for, like in this? Because if you, I mean, if you have like this piece of Weyl semimetal, you have just like, okay, you have your Weyl electrons inside the material, but then you have like the surface.
The Fermi arcs.
Exactly.
Yeah.
And how are they accounted for? I mean, I mean, which electrons are like behaving hydrodynamically? How can you, all of them? I mean, how can you distinguish that?
Well, in this experiment, I don't think that they were able to distinguish between surface and bulk electrons. And also, I'm quite sure that they were not taking into account the formation of the Fermi arcs explicitly. So this type of calculation is based just on the bulk current profile. Actually, it would be quite interesting to pinpoint the formation of the electron fluids on Fermi arc surface states, but it might require a different, say, different regime or different range of parameters to form. Actually, we investigated this problem in one of our papers. It might be possible to realize, for example, hydrodynamics in the bulk, but not on the surface, and vice versa, because Fermi arc electrons and bulk electrons feel say different disorder potential, so they scatter differently. So in general, one can have a decoupled fluids in the bulk and on the surface, but in this type of experiments, I don't think that they were studying this in detail. So they just use a bulk current to claim similarity between the observed and measured magnetic field profiles. But yes, this would be interesting to do.
Okay, thank you.
So all these experiments motivated us to investigate what are interesting properties of electron hydrodynamics in Weyl semimetals. We started this a few years ago, and recently we decided to return to this type of problems and investigate various instabilities that could appear in hydrodynamic flows of Weyl and Dirac semimetals. So let me start with the first paper where we investigated the electron convection. So to start with, of course, let me define what convection is. So here I'm showing the simulation of convective flows in a finite film of Weyl semimetals performed via COMSOL. Convection appears convection can be defined as a motion of fluids that appear because of two ingredients, inhomogeneity of the fluid and with the presence of some external force. In this case, we do have a temperature gradient. So we have a hot bottom surface and cold top surface. And also we have a gravitational force. Other examples of convection are well known to you, for example, boiling water, heaters. In this case, the hot fluid becomes less dense and start to move upward. And cold fluid is quite dense compared to the hot one and starts to move downwards. As you can see, for example, here is the central part of this simulation. Also, convection is very important not just for heating our houses and preparing coffee, for example. It's also very important for Earth's climate. Convection also occurs in magma and plays an important role in transfer of heat between core and crust. Finally, convection is even manifested on the stellar length scales. For example, convection appear in our sun and transfer energy from radiative zone to the surface of the sun. So examples of convection are quite ubiquitous and we often meet them in our everyday life. However, convection is not just a simple motion of fluids that appear because of forces and homogeneity. As you can already notice from this simulation, convection leads to the formation of some certain patterns in the fluid. Indeed, by taking a snapshot of this figure, we see that there are several convection cells in this layer of the fluid flow. For example, here our fluid moves upward, here it moves downward, again upward and again downward. And if I consider a large film, I will have a long train of these convection cells. So here I'm showing just a simple type of convective instability, namely the roll type of instability. However, when we include some other effects related, for example, to boundaries and to surface tension, we can have a more complicated pattern of convection cells. For example, here I'm showing the observation of convection cells on the surface of our sun. As you can see, they form something quasi-periodic, but still quite interesting. In order to realize such convection cells, it's not enough just to heat fluid by any amount. One needs to reach a certain threshold, which is determined by the critical Rayleigh number. So what is Rayleigh number? Essentially, Rayleigh number determines how effective is diffusion compared to viscosity. So it's defined as a time scale for diffusion divided by time scale for convection. Time scale for thermal diffusion essentially is just size of the system divided by thermal diffusivity. And as for the viscosity, we can determine the corresponding time scale via the viscous Dirac force. So by doing some simplifications and assuming thermal expansion, we arrive at this expression. So essentially, a Rayleigh number is determined as a multiplication of force, system size, temperature difference, and it is inversely proportional to the viscosity. Indeed, the more viscous fluid is, the harder it is to steer it and achieve some motion of this fluid. All these beautiful hydrodynamic effects motivated us to take a look whether it's possible to achieve hydrodynamic convection in electron fluid, Weyl semimetals. In particular, our motivation was that if possible, convection will provide a new characteristic hydrodynamic feature that could be used to pinpoint the hydrodynamic regime of transport. Furthermore, convection might be used to effectively cool our modern electronics. Indeed, because convection is much more effective than, for example, thermal diffusion. So this would be instrumental in creating various microcoolers for our modern electronics. To answer these questions, we use the following model setup. So essentially, we considered a slab or film of Dirac or Weyl semimetal subject to an external electric field, which is defined by the voltage difference, and temperature gradient, defined by temperature difference. To describe the formation of convection cells and define the convection threshold, we write the following system of hydrodynamic equations. So here, the first equation is essentially the Navier-Stokes equation, which includes the advection term here. It includes the viscosity terms here. There is also a term that is responsible for the momentum relaxation in due to the scattering of impurities and phonons. Finally, there are terms related to the pressure gradient and external forces on the right-hand side. Also, the system of hydrodynamic equation needs to include the electric charge continuity equation, energy continuity equation. Here, currents are defined as follows and include viscous components and components related to the non-hydrodynamic part of the distribution function. Particularly, this are dissipative or called dissipative correction. However, there is a significant difference between neutral fluids and electron fluids. Electron fluid is a charged fluid. Therefore, one needs to include Maxwell equation in order to describe its properties carefully. In our case, we consider slow flows, and we could include only the Gauss law from the set of Maxwell equations. Here already we started to think that, there might be strong differences between the formation of convection cells in neutral fluids and electron fluids, because usually one doesn't take into account this Gauss law. And to find out the threshold for convection, we solved the system in 3 stages, essentially. First stage is to determine equilibrium state, which is sort of trivial. We just define the equilibrium state without any flows and any motions. Second step is to determine the temperature and distribution and electric field in the steady state. So in this case, essentially, we solve the system without any hydrodynamic flows. We found that temperature acquires simple linear dependence on the widths on the coordinate along the slab, as you can see here. So there is a constant temperature gradient along the slab. Also, we found that the field is quite strongly screened in material, and deviations of the charge, electric charge density, are vanishing inside the slab. Of course, there are quite noticeable deviation near the surfaces, but since we're interested in the bulk properties, they could be ignored. Finally, as a third step is the most interesting one. It's related to finding out small deviations related to hydrodynamic flows. In such case, we assume that there is a certain hierarchy of scales. In particular, equilibrium values are large compared to the steady state values, and steady state values are large compared to the hydrodynamic values. So, performing the expansion in weak variables, we obtained the following system of equations that describes the hydrodynamic deviations. We use an approximation that is reminiscent to the famous Oberbeck-Busenex approximation in fluid dynamics. In this case, we assume that all deviations of the densities and other thermodynamic parameters are small and can be ignored. Only one of them is important. Particularly, it is related to the buoyancy force. So if you have a force which is multiplied by the deviations of hydrodynamic density, then the system should not be ignored. And it's actually a core of Busenex approximation. The other important term is related to the advection term in the energy continuity equation. Other equations are the charge continuity equation and Gauss law. So there is nothing interesting there. But they are important in order to correctly describe the diffusive part of the transport. In order to investigate the stability, in order to perform the stability analysis, we use the conventional plane wave ansatz. As you can see here, we assume that all hydrodynamic variables are periodic in space. So here I am, for example, separating the normal component of the wave vector and perpendicular component that lies in plane of the slab. By substituting these ansatz to the system, and solving the corresponding set of equations, which is quite lengthy, but it's doable, we derive the following equation. So what this equation is about? This equation relates the components of the momentum, components of the wave vector, K, to properties of the system. In particular, it contains a Gaussian length, which quantifies the momentum relaxation. It contains the Thomas Fermi wave vector that is related to the Gauss law and is actually a novel feature of electron hydrodynamics. And also we have a Rayleigh number here, which in the case of our fluid inside Dirac and Weyl semimetals is given by a rather complicated expression, but essentially it boils down to the same expression that can be derived for a regular fluid. So it's proportional to the force, size, temperature difference, and inversely proportional to the viscosity of the fluid. The strategy to determine whether we have a convection or not is just to solve this equation for the perpendicular component of the momentum, K perp, as you can see here. If we have a real solution for this component of the wave vector, then we have a periodic cells. If the solution is imaginary, then we don't have any sort of periodicity in plane. So we have a diffusive regime and no convection cells are formed. However, it's more convenient to a little bit rotate the problem and rewrite it in different terms. In particular, we can just invert this equation and write down the following form. And we can ask the following question. What is the minimal Rayleigh number that we should reach in order to achieve any convection? For this, we minimize the right-hand side of this equation and determine the value of the real wave vector, K perpendicular. And then we substitute this value again into this expression, and this will give us the minimal number, Rayleigh number, that is needed to achieve a periodic solution. Then this will give us the estimate of, for example, temperature gradient that we need to apply in order to get a convection. So for small temperature gradient, there will be no convection. For a larger temperature gradient, some convective solution might appear. In order to determine Kx, since we consider a finite slab, we need to apply boundary conditions. We assume simple boundary conditions that are related so we just assume that temperature deviations vanish at the surfaces, and we assume that there are no normal fluid flows through the side surfaces. In this case, the solution for Kx will be quite trivial, just PL divided by the size of the system, where L is just an integer number. Then performing the procedures that I just described, and assuming for simplicity that our Thomas Fermi wave vector is much larger than the inverse size of the system, and also just assuming that the system is large comparing to the Gaussian length. So these approximations essentially are not necessary, but are quite useful in order to get an analytical simple expression. In this case, we got the following estimate for the minimal, well, not minimal, I would say that this is some sort of zeros Rayleigh number, which is actually even larger than the minimal. And we got the following number. So as you can see, this number is rather large, but large compared to what? We need to provide some scale in order to compare with. And this scale is given by the conventional Rayleigh number that is needed to realize convection in neutral fluids. So in neutral fluids, what do we have? We have vanishing Thomas Fermi wave vector, and we have an infinitely large Gaussian length. In this case, we can solve rather easy this problem and obtain the following minimal Rayleigh number without any approximations, actually. So it's of order of thousands, but this number is of order of 10 to 22. Well, so we already started to understand that there is some problem. However, it might be still the case that the actual Rayleigh number that we are achieving by applying temperature gradient will be also large due to some reasons. For example, therefore, it's important to provide the actual Rayleigh number. So here is the estimate, and here are essentially plots for the minimal Rayleigh number and actual Rayleigh number. So minimal Rayleigh number essentially is given by, well, not this expression, but by the more complicated expression obtained by minimizing this solution, given by the solid lines here. And the actual Rayleigh number that we are achieving by applying some temperature difference of order of T0, some rather large screened field of order of 10 volts per meter, as a function of system size is shown by these dashed lines and field regions. So as you can see, there are many orders of magnitude difference between these numbers. Notice that I am using logarithmic scale here. Even for very large systems of centimeter size, we still have several orders of magnitude. And even for very low doping, again, there are several orders of magnitude. So the bottom line is that convection instability is strongly suppressed in three-dimensional Dirac and Weyl semimetals, principal other materials too. The reason of the strong suppression is simple. And is related to the Gauss law and Coulomb forces. Indeed, the core of convection itself is expansion, thermal expansion of the electron fluid. And this thermal expansion immediately leads to the generation of some screening field via Gauss law. Therefore, in charged fluids, thermal expansion is strongly suppressed. And this actually leads to the fact that we need to apply an extremely large, either extremely large thermal gradient or extremely large electric fields to the sample in order to achieve something that is reminiscent of the convection instability. Therefore, we concluded that convection is literally impossible in three-dimensional materials. What about 2D, you could ask, because in two-dimensional materials, Coulomb forces are usually weaker, and screening is weaker than in 3D. We also calculated the corresponding minimal Rayleigh number in the case of graphene by using the so-called gradual channel approximation, where the field is proportional to the gradient of density. In this case, we found that while this expression for the minimal Rayleigh number looks quite similar to that in 3D, there is one very important difference. So one can notice that here we have a Thomas Fermi wave vector, which enters together with wave vectors here. But here we just have an overall multiplier. Therefore, to make long story short, the presence of the Coulomb forces also inhibits convection in two-dimensional materials, but the effect is less dramatic than in 3D. Still, however, this coefficient could be quite large and can give 2 orders of magnitude. So by using the parameters for graphene, for example, we estimated minimal Rayleigh number and actual Rayleigh number to be, well, not different by several orders of magnitude, but still different. Therefore, we concluded that while Coulomb forces could inhibit could play a quite important role in inhibition of convection in two-dimensional materials, it is disorder and scattering, momentum relaxation, that inhibits mainly the convection in two-dimensional. It's quite noticeable that convection instability in graphene was investigated before. However, both of the inhibitors, in particular Coulomb forces and momentum relaxations, were not taken into account. And it was predicted that in principle, it might be possible to achieve convection in clean, large samples. But if one takes into account these 2 inhibitors that I just named, then one gets, again, several orders of magnitude difference. Maybe not 10 orders of magnitude, but still 2 or 3 orders. And of course, this makes convection quite improbable in graphene too. Not impossible, but highly suppressed. So we have a somewhat negative result, but still it can teach us an important lesson that not all hydrodynamic phenomena can be realized in usual fluids like water necessarily appear in electron fluids. And there are important differences, which is interesting to clarify before doing any experiments. This motivated us to take deeper whether there are any other interesting instabilities in Dirac and Weyl semimetals, in particular those related to non-trivial relativistic-like dispersion relation and quasi-particle spectrum. So for this, we investigated the so-called current-driven instabilities that could appear when material is subjected to a direct background current. And we did found one. We did found that there is a novel type of instability related to entropy waves. In order to understand what is this instability and how it appears, the natural starting point will be the eponymous Jakonov and Schur instability. So in the 1990s, Jakonov and Schur proposed a rather simple model of a current-driven instability for plasmons. They used a two-dimensional electron gas, as you can see here, which was subject to a gate and applied rather non-trivial boundary conditions for this electron gas. They also used the hydrodynamic approximation and gradual channel approximation. So in the simplest hydrodynamic model, so essentially they needed to solve only two equations. Navier-Stokes equation, they just ignored viscosity, so just Euler equation, and continuity equation. In the gradual channel approximation, the voltage, gate voltage, is related to the density in this two-dimensional gas. So if one solves the system in the infinite case, when the size, where the distance between source and drain is large, then one will get a conventional plasmon relation. So we have a linear in momentum dispersion relation for plasmas, which is conventional in two-dimensional gas. However, the core of this Jakonov-Schur instability is in the boundary conditions. So they assumed very unusual, but principally realizable boundary conditions, where the drain, for example, is subject to an infinite impedance. It has an infinite impedance. This could be achieved, for example, by coupling it to a large coil. This means that all oscillations of current there are vanishing. On the other hand, the source is grounded. In other case, this means that the voltage oscillations vanish the source. And also, the sample is subjected to some background electric current, as you can see here. So first, they found that plasmons become discretized. So instead of the simple dispersion relation, we get a discretized plasmon, which also feels the background velocity. But the most interesting part is that there is an imaginary part of the plasmon frequency now. And moreover, this imaginary part is not just negative, as we expect for example, for diffusion or disorder effects, but it could be positive. This means that plasmon mode could become unstable. It grows with time. Of course, we can't predict what will happen after a long period of time. For this, we need to solve a nonlinear equation, which will probably determine us the state entered by this plasmon in the end. But still, we can describe well an onset of the plasmon instability. Furthermore, this plasmon instability has a very interesting and there's a simple explanation. Therefore, I would like to briefly outline it. So the system that I just discussed before, it can be understood as electron plasma subject to two mirrors. Left-hand side, where we have vanishing potential deviations, is essentially an ideal mirror with a unity reflection coefficient. The right-hand side, where we have vanishing current oscillations, is essentially a mirror with a non-unity reflection coefficient which depends on the difference of velocities. So essentially, this is just like a static mirror and moving mirror. If we have a plasma wave that propagates through the system, the time between the reflection is given by the following expression. Then we can simply calculate the growth of the wave amplitude via this relation. So essentially, we can count how many times plasma is scattered from mirrors, multiply the scattering coefficients, and number of times that we should multiply is equal to the number of times our plasma completes the full period in this structure. Then, by solving this simple equation, we arrive at the Dirac instability expression. So recently, there is a huge surge of interest towards this Dirac instability. The reason is very simple. The frequencies of these plasma waves lie in the terahertz range. Therefore, if we have instability, we have an enhanced emission of plasmas from the system, plasma waves from the system. So we can have a source of terahertz radiation just by supplying our specific structure by a DC electric current. Well, this is a very interesting proposal, but well, unfortunately, to the best of my knowledge, there are no experimental confirmation of the emission of terahertz radiation via this instability. On the other hand, we can have an inverse process where we are detecting terahertz radiation via the DC electric current generated in such a structure. This case was indeed observed experimentally. Just briefly, I would like to say that they saw the DC current generated by terahertz radiation, and the experimental curves for the responsivity matched very well the theoretical expressions. So there is a hope that at least in a detector mode, we are able to observe the Dirac instability. So this motivated us to investigate this instability further and try to find out whether there are any interesting features related to the relativistic-like spectrum of our Dirac and Weyl semimetals. For this, essentially, we use the same system of equations that I already presented before. We even simplified it more by dropping the dissipative corrections to the currents. By using the linearization on top of the background flow, we found the following modes in the infinite system. So we found in 3D that there is a gapped plasma, and there is a gapless plasma in 2 dimensions. However, unlike previous studies of the Dirac instability, we also included the energy continuity equation in our system. And this led to an additional collective mode, which is known as the entropy wave mode. Essentially, this is a downstream mode that propagates with the flow velocity, as you can see here. In this mode, we have vanishing oscillations of the fluid velocity, and we have the following relation for the density and energy oscillations, which follows from the fact that the pressure gradient and electric Coulomb force compensate each other. So this mode looked quite unusual to us, but then we found that there are many similar modes in physics. Among them, for example, I would like to briefly stop on the so-called geostrophic currents, which also appear because, which also have a vanishing frequency, and they appear because pressure gradient and Coriolis force is compensated. In such case, one will have a rotating fluid. For example, these geostrophic currents are related to formation of gyres in oceans. Gyres is just a circular flow, which can be regarded as a collective mode with vanishing instability. And these gyres are very important in explaining why, for example, the ocean near California is quite cold. It's much colder than it should. So there is this faint link to other collective modes. However, returning to the stability analysis of our entropy waves, So now, what should we do next? The Jacob-Shor instability appears because we have very non-trivial boundary conditions. In our case, we also need to apply boundary conditions. We use the standard Jacob-Shor boundary conditions and also supply them with an additional boundary condition for temperature. We found that plasmons, well, I'm considering third dimension so far, plasmons become unstable with the following instability factor. So this agrees more or less well with the analysis of Jacob-Shor instability in the literature. However, we also found that entropy wave instability becomes unstable. Entropy wave becomes unstable with the instability parameter, which is even parametrically larger than that for plasmons. Indeed, by comparing these two terms, we found that the instability parameter for the entropy wave is determined by this factor, which is usually large, since the plasma velocity is quite large for doped Weyl semimetals. Furthermore, we found that there is no entropy wave instability for non-relativistic fluids. So if we just solve the system of hydrodynamic equations assuming a non-relativistic spectrum, we find that the entropy wave remains stable. Well, for being quite surprising, we were able to track this finding to the following difference between non-relativistic and relativistic fluids. If we take a look at the system of equation for relativistic fluid, we can see from the Navier-Stokes equation, we can see that hydrodynamic flow of relativistic fluid is a flow of energy rather than a flow of mass as in the non-relativistic fluid. Therefore, in non-relativistic fluid, the energy continuity equation is an auxiliary equation rather than an important equation that mixes flows and entropy waves. So in other words, in non-relativistic fluid, entropy wave remain decoupled from the rest of the system. But in the relativistic fluid, because of mass energy replacement, entropy wave becomes somewhat coupled to the rest of the system. Therefore, since the plasmons acquire instability, entropy wave also acquires instability. We supported our analytical results via numerical calculations. Here I'm just showing a few branches of entropy waves, and I'm using razor thin film. Plasmons and entropy waves are shown by red dots and blue squares. Black lines and magenta lines are analytical results. So we see a good agreement. Of course, we have plasmons with a frequency that is larger than plasma frequency. We have entropy waves which rise linearly with fluid velocity. But what is most interesting is that you can already see that instability increment is much larger for plasmons, for entropy waves than for plasmons. Furthermore, the entropy waves and plasmon appear for different directions of the flow. It's another difference. Finally, one can take a look at the oscillating variables in the plasmons and entropy waves. For plasmons, for example, one can see that all variables oscillate: fluid velocity, density, energy. In the case of entropy waves, however, the velocity oscillations are vanishingly small compared to other oscillating variables. Furthermore, we have a noticeable localization of entropy waves at the end of the wire where we do not fix temperature. So in addition to different dependence on the flow velocity, we have different spatial localization and different oscillating variables for plasmons and entropy waves. Finally, in 2 dimensions, we have a very similar picture. We also have an instability of entropy waves. And here is a key difference, however, is that we don't have a plasma frequency to define the frequency scale. Therefore, we are using size of the system. So since my time is running out, I'm proceeding to conclusions and summary. First, we found that due to screening effects, the convection instability is strongly suppressed in 3-dimensional electric fluids. Momentum relaxation effects and screening are also important in 2D, and they are the main inhibitor factor. This allowed us to conclude that convection is impossible, almost impossible in 3D, and highly suppressed in two-dimensional materials. In the second part of my talk, I discuss the formation of the various instabilities driven by external currents. In particular, under specific boundary conditions, we confirmed that the current-induced plasmon instability, namely Dirac-and instability, can be realized for three-dimensional Dirac and Weyl semimetals. We found also that in systems with relativistic-like dispersion relation, it's possible to have a novel type of instability, namely the entropy wave instability. Since the frequency of entropy waves depends strongly on the fluid flow, essentially external electric current, it might provide a tunable source of radiation. Finally, before concluding, I would like to discuss maybe a few questions that should be still addressed in relation to the instabilities. For example, I have the following questions. Are there any interesting non-trivial manifestation of band dispersion in the hydrodynamic regime other than the entropy wave instability? So since the suppression of convection relies on Coulomb forces, can we have instability for other quasi-particles, convection instability for other quasi-particles, such as magnons or phonons, for example, for which the hydrodynamic regime could be in principle possible? What is the role of magnetic and pseudomagnetic fields in the instabilities, both current-driven, convective, other? Chiral anomaly can be important here, for example. Other questions include, can we realize instabilities in kinetic regime, not hydrodynamic regime? What's the role of chiral charge? And many others. I'm open for discussion, and I hope that Polnas B's fellowship will allow me to continue this discussion and collaborate with local researchers at Wrocław Institute, Wrocław University of Technology. Thank you very much for your attention.
Thanks a lot for the nice talk, Pablo. So I think, okay, now it's time for questions. We have a few minutes for some questions. So please, if any of you have a question, just go on and ask.
Maybe I can ask one question about this experiment that you mentioned. So
which one?
The hydro experiment in various semimetal by Weyl.
This one.
Yes.
Okay.
So, I mean, I agree with what you said. I would expect that somehow the bulk and the boundary properties should be different. So then how they can probe bulk properties with like scanning something on the surface, because I can imagine that it works for like 2D materials, but for 3D, the Poisson flow should be in the bulk. Like there should be like, you know, probably like a boundary that doesn't move and, you know, something inside that flows, but somehow here they plot something that looks like 2D. Do you have like any intuition how
yes,
it works?
So first of all, they're somewhat cheating with claiming the observation of hydrodynamics in 3D, because they do have a thin film. So while being quite thin in order to allow for a one-to-one correspondence between the current and magnetic field, because we know that in 3D we cannot restore current by measuring magnetic field. It was claimed that the film is sufficiently thick to allow for the bulk states and bulk transport. So, but what do they measure? They essentially do not measure the surface properties of the film. This tip, it moves quite far away from, well, not far away, but it doesn't probe the surface property. It probes the total magnetic field generated by total current that flows through the sample. it seems that it is assumed that the surface contribution in this material is either negligible compared to the bulk current, or yeah, probably it's just they just neglected it. Because I agree with you that well, in Weyl semimetals we can have Fermi arcs, for example, but even in usual materials we can have surface states that might lead to some additional contribution to current, like surface currents. And this could lead maybe to some additional contribution to the magnetic field. But here it was assumed that the response is dominated by the bulk current.
Okay, well, thanks.
At least this is my point of view. Maybe they think differently.
Another question? Well, meanwhile, the people decide if they want to ask something else. I have it's like a naive question. So I didn't understand at which step in your computations, in the first part and the second part, it was important for the system to be Dirac-like. Because in the end, you were just like solving Navier-Stokes equations in a charge system. But I don't know, I missed the input where the electrons had to be relativistic.
Okay, for convection instability, it is not important to have a relativistic fluid. But where the relativistic comes into this system is a form of the Navier-Stokes equation. This is a relativistic Navier-Stokes equation. With we do have energy here instead of mass density, for example. But in the case of convection instability, it is not important to have a relativistic fluid. So we can just use a conventional Navier-Stokes equation and we will get qualitatively the same result. So,
but if you have, even if you assume that you have like a Dirac material,
yes.
In the end, you have to assume that velocity is small, and then it should reduce in something non-relativistic like. Or
well,
am I missing something?
Well, still, I think that there will be difference. So even if I assume that the velocity is small, I'm replacing mass density with enthalpy density here. And they have a different dependence on the chemical potential, temperatures, for example. So so the question would be different. As I said before, the transport of the hydrodynamic transport in non-relativistic systems is a transport of mass. But in relativistic-like system, Dirac and Weyl, it is a transport of energy.
So I guess what you are saying is that the important input is that you are not assuming Galilean invariance. Therefore, the charge current is an independent object to the momentum density. Is that what you are saying? See, because the point is that if you have Galilean invariance, then as you said, the mass current and the momentum density are basically the same thing. And then here, the continuity equation for charge is like completely independent to the momentum conservation, which is just a statement, of not being Galilean invariant.
Yes, that's true. Because yes, there is such thing in non-relativistic hydrodynamics. You're right that the essential Navier-Stokes equation for the conservation of momentum is strongly related to the conservation of charge density. So they're somewhat coupled because the current is a current of mass, of density. But in the relativistic systems, it's not the case as far as I can remember.
Yeah, no, that's right. So so that's what I was trying to understand. What's like the relevant input here that distinguishes your analysis from just like a normal metal. Okay, so I was wondering why he's just talking about like a Dirac metals instead of just like a normal metal in some hydro regime. And then since I'm understanding your answer is just because your charge current is not the mass current, basically.
Yes, it's true. Well, as I said before, that in the case of convection is maybe not that important. Well, that's something that we found. So one can do the same calculation for non-relativistic fluid, and by taking into account the Gauss law, one will get the same result. The convection is suppressed. But in the case of this stability, here it was actually quite important to consider a relativistic equation. And actually, we have quite lengthy calculations where we deal with the dependence on the fluid velocity of energy, density, chemical potential, temperature. So it's not that easy, actually, not that straightforward. So yes, there is a qualitative difference, at least in the case of current driven instabilities. There, it's important to have Dirac and Weyl semimetals. In the case of convection, probably no. You're right.
Okay.
Not that important.
Okay. Okay, I think I will just, so well, we can officially thank Pavlo again and conclude like this official part of the seminar. And I will stop like